EPFL Explore was founded early in 2020 at EPFL. The goal was to build a rover capable of moving on complex terrain and performing scientific tasks with the help of a robotic arm. A project can quickly spin out of control if it is not well organized or if it doesn't have a guiding thread. The European Rover Challenge presented both a great objective to aspire to and a set of constraints to work with. To achieve this goal, we have assembled around 50 students from diverse backgrounds. The team is organized with a president, a project manager, 2 system engineers, 8 technical subsystems, and 2 non-technical subsystems. The control station subsystem receives the telemetry from the sensors and cameras on the rover and sends commands to control the different onboard subsystems. All the data from the various sensors of the rover are collected by the avionics subsystem, in charge of designing the onboard hardware and software. The handling device subsystem builds and controls a multiple degrees of freedom robotic arm for object manipulation and detection, as well as sample recovery. The structure subsystem's role is to design a reliable chassis able to overcome all types of challenging terrains. It also has to ensure that all the modules of the other subsystems can be correctly integrated on the rover. The navigation subsystem is in charge of controlling the in-wheel motors, creating a map of the environment and navigating through it. The power supply subsystem manages the power distribution to the different components of the rover, as well as the safety through the emergency button and circuits.
For our scientific plan, we want to find the traces of water on the Mars yard. We are searching for mineral assemblages which indicate water-based processes, specifically carbonates and phyllosilicates. They are identified by density, particle size, and color. There's only limited information we can extract from a single image of the Mars yard, so a physical soil sample would be an invaluable asset for the Martian mission. Here we present our science bay. This is where Argos will keep its golden fleece. We first load the soil sample into the container using our handling device. Right after the loading process, the mass of the soil will be displaced automatically in our control station. Meanwhile, an image is captured by an in-situ pinhole camera and wait to be analyzed. The motor will then seal the container and get ready for the next sample. Our bay has the capacity of 3 soil samples, each corresponds to 1 probing location. During the post-traversal session, our control station will process the received image and provide our geologists with the necessary data. Once we retrieve the sample back on the Earth, the geologists can then perform more detailed examinations.
The 6 wheels, powered by brushed DC motors, allow the rover to drive forward and backward, as well as to turn right and left, thanks to differential steering. With the differential bar and the rocker bogie mechanism, the rover is able to climb slopes greater than 20 degrees and cross obstacles up to 15 centimeters high. The operator is assisted by 2 cameras to drive the rover, the navigation camera on the top of the mast and the belly camera pointing on the wheels. All the data of the various sensors of the rover are sent to the control station through a 5 GHz omnidirectional antenna and displayed on the graphical user interface. In manual mode, the driver operates the rover using a game controller. In case of unexpected behavior of the rover, it can be stopped instantaneously by pushing on the red emergency button. This button completely disconnects the main power supply from the unique battery thanks to an automotive relay. To indicate the state of the rover, an LED is toggled when the rover is in operation. The control station can always set the rover's state, regardless of the operation it is performing. The manipulation, probing and science tasks are performed using an end effector mounted on a 6 degree of freedom robotic arm. This handling device allows the operator to manipulate a control panel remotely. Rotary switches and toggle switches can be easily turned on and off. Using an embedded analog to digital converter, the arm has the ability to measure voltage from a standard plug and display it in real time on the control station. A depth camera mounted on the forearm makes the control of the gripper easier and allows to detect and recognize elements on the control panel. The handling device can also be used to place probes vertically in the soil. The ability to turn the gripper while pushing the probe ensures that it is correctly secured in the ground. After the probes have collected the required data, the arm can remove them and store them back in their dedicated container. To recover soil samples, additional 3D printed scoops can be added to the end effector. The samples are then carried to the science bay where they will be carefully analyzed. Using state-of-the-art technologies, Argos is the hard work of many EPFL students who spent days and nights developing it. We are proud to participate at ERC 2021 and represent Switzerland for the first time in an international rover competition.